Hi everyone. Last time we were looking at antiderivatives, we were able to come up with the formula that if f of x is some function where it's a nice polynomial looking thing, or really x to any power n, we could find its antiderivative using the formula the antiderivative of f is 1 over n plus 1 x to the n plus 1 plus c. We can quickly test this out to remind ourselves by taking the derivative here. Derivative of c is 0. Derivative of this, you bring the n plus 1 down, those cancel, you subtract 1 from the power, and you get x to the n. This was particularly useful for us with lots and lots and lots of different types of functions. For instance, if you had something like g of x, which is equal to the square root of x, we could say that's x to the 1/2. And then from there, we can say that the antiderivative of g has to be x to the 3/2, because we add 1 to the power. And then we put 1 over that new power, 1 over 3/2, which is the same as saying 2/3 x to the 3/2. Of course, we'd then need our plus c at the end, because remember we have infinitely many antiderivatives here, not just one. In today's video, we're going to look at two different types of antiderivatives that we haven't looked at so far. The first type is going to be a recognition antiderivative. So you see a particular function, and you happen to know already through past experience that it must be the derivative of a particular function. The second is going to be the reverse chain rule. And the reverse chain rule is pretty tricky and takes a while to get the hang of, but once you do, it works out really well. But we're going to start today with some derivatives that you should know. So then we can get the antiderivative. So let's start with this particular function. F of x is 1 over 1 plus x squared. What's the antiderivative? Well, none of the techniques that we have so far can help us answer this question. But from last term, you should have seen a function whose derivative is this. Can you remember what function that is? Hopefully, you were able to tell me that that function was inverse tangent, and then of course we'll add the plus c. We recall that the derivative of inverse tangent is 1 over 1 plus x squared, so the antiderivative of 1 over 1 plus x squared must be inverse tangent. Let's try another one here. Let's say g of x happened to be negative cosecant x cotangent x. Do you know what the antiderivative is? Hopefully, you were again able to correctly identify that this happens to be the derivative of the function cosecant x, and of course plus c. Again, it is very important that we remember all of our derivative rules and patterns. While we could go through and rederive these derivatives for ourselves, it would be more efficient to have them memorized as we derived them already in class. That being said, if you do forget them, you could always go back and rederive them, and we can talk more about that during class. So these are what I was calling the you should be able to look at it and know antiderivatives, right? Look at it, there's not a whole lot of work that you can do other than recognize, yes, this happens to be the derivative of arctan. Great. These types of things will come up with natural log, knowing that its derivative is 1 over x, with e to the x, knowing its derivative is e to the x, and with all of the trig functions as well, and the inverse trig functions. But okay, now that we have that settled, not a whole lot of instruction we can do on that one other than remember, we're going to focus on the inverse chain rule for most of this. So you might recall the chain rule says that the derivative of f of g of x is f prime of g of x times g prime of x. So anytime we see a function, we see an original function that looks like this, that has this form, we're going to think to ourselves, all right, this has to be inverse chain rule. Sometimes we call this anti-differentiation by substitution. So, since I've used f and g already, I'll give my function a new name. I'll call it h of x. And for this particular function, I'm going to let it be 3x squared divided by x cubed plus 1. Okay. Here's my function. Now here's my goal. I want to identify each of these parts, f prime, g, and g prime. So it might not look right now a lot like the chain rule, but I can just rewrite it so that this multiplication exists if I rewrite it in the following way. 1 over x cubed plus 1 times 3x squared. By rewriting it in this way, it looks much more identical to the chain rule, right? Where this looks like our g prime, and this looks like our f prime of g. So I'll make a side note to myself. Hey, if g prime is 3x squared, that's tough because I don't know exactly g. So my goal should be, can I find a function in here somewhere whose derivative is 3x squared? And I can. This denominator, x cubed plus 1, its derivative is 3x squared. So if I let my g of x be x cubed plus 1, I already have my correct g prime of x. G prime of x is just 3x squared. So I need to figure out this last part here, this f prime. I know f prime of g of x is 1 over x cubed plus 1. So the question is, if f prime is 1 over that, what function, when you take the derivative, gives you 1 over x? Right? In this case, 1 over g of x. Right? Because I know to myself, f prime of g is just 1 over x cubed plus 1. So f must somehow be, something whose derivative is 1 over a function. And perhaps you recall that 1 over x is the derivative of natural log. That should tell us that if f is natural log and g is x cubed plus 1, ideally we have found our function here. So let's test this out. It's looking like h of x, which should be f of g of x. Well, f we decided was natural log because f prime was 1 over the function here, 1 over g of x. G is just x cubed plus 1, so our capital H should be natural log of x cubed plus 1. And then, of course, we'll get the plus c. Let's test this out to make sure we are right. Remember, you can always test out the antiderivatives just by differentiating. So let's do that quickly. If we take the derivative of h of x, we get 1 over x cubed plus 1, that's the derivative of natural log, times the derivative of the inside, 3x squared, and then the plus c becomes 0. This derivative is exactly the function we started with, h of x. That's really good. That tells us that we did it correctly. And in fact, capital H is the correct antiderivative for lowercase h in this case. Now, as I mentioned at the beginning of this video, this is a very tricky process to get a handle on, but once we do get a handle on it, we'll be able to use it very effectively to find antiderivatives of many more complicated functions. Let's try to do another one here together. So, I'll start out with a function, and that function is going to be the square root of 1 plus sine x times cosine x. Okay. Again, my goal is to locate the inside function, the outside function, the inside function's derivative, all of these things. So I notice that the cosine of x should be my g prime. And I want to find the biggest possible function written inside here whose derivative is cosine of x. Well, that's 1 plus sine x. So here we go. My g of x is going to be 1 plus sine x. My g prime of x is going to be cosine of x. That means my f prime of g of x is the square root of g of x. So if I want to find the original f, well, I just need to find the antiderivative of the square root. So if I think of this as g of x to the power 1/2, just as in the problem we saw earlier in this video, its antiderivative would be 2/3 g to the 3/2. So my antiderivative of h, which is capital H of x, should be g, which is 1 plus sine of x, to the power of 3/2, because I need to increase this power by 1, and then I need that 2/3 out in front, so that when I bring this power down it'll cancel, because originally there was nothing in there, and then a plus c. So, again, we can check this by doing our differentiation. If I wanted to find the derivative, d over dx, of h of x, I'd bring down the 3/2, it will cancel with the 2/3, so I'll just get 1. So I have 1 plus sine x to the power of 1/2, and then I need to multiply by the derivative of the inside, so times cosine of x. And that is exactly the lowercase h of x that we started with. So fantastic. Turns out that this one works as well. Again, I cannot stress enough how tricky this is the first few times that you try it. I expect that there's some confusion, even as you're done watching this video. But try to take careful notes and try to do some practice problems on your own to see if you can follow these steps to solve this problem. Maybe I'll write one more function for you here, and I'll just leave it up there for you to try to solve on your own, and we can chat about it next class. Let's say h of x happens to be, I don't know, something like e to the power of pi x times pi. This is a more basic one, but it still follows the same properties. So hopefully you can figure out how to take the antiderivative of this one just by using the formula and what we've chatted about in this video.